Hello, my name is Pınar. I will be presenting a summary of my latest research results about major climate change and magnetic polarity change prediction for Earth based on a circular orbit model I have proposed previously. So here is my interactive presentation for the International Astronautical Congress 2025. The title of my paper is Impact of Earth-Sun Orbital Variations on Climate Change and Magnetic Polarity of Earth. This is based on a circular orbit model I had previously proposed. I have published this in my book on Amazon. You can access by the link on this top left pane. I have presented this in COSPAR 2021, which was also in Sydney, Australia. Hi. And you can access that presentation again on the top left pane here. So here in this pane, I have provided a basic Earth and Sun orbit configuration, not scale, to give an idea of how the orbital parameter calculations have come out as a result of my research. If we take the horizontal plane to be the orbital plane of Earth, the Sun has a circular orbit plane which is tilted by beta degrees, which is minus 156.56 degrees from the x-axis. That amounts to 23.44 degrees from the minus x-axis. We can imagine the Sun to have revolved all the way here, the orbit. And the dates for the equinoxes and the solstices are the quadrants of its individual circular orbit for the Sun. But it's shifted for the Earth because they have a phi-0 phase shift of approximately 151 degrees. So the June 21 and December 21 line is a solstice line for the Sun. So in this coordinate system, the Earth is moving counterclockwise with respect to the z-axis. Earth's north pole points down along minus z-axis. The Sun is moving clockwise with respect to the positive z-axis with a tilt, and its north pole is pointing up with this tilt here. We know by observation that the Sun and Earth have different year cycles. The major one, which is used, is the tropical year, which is the time it takes for the Sun to complete one cycle with respect to the Earth, from solstice to solstice or equinox to equinox. A sidereal year is a time for the Sun to revolve 1 year and come back to the same position with respect to background fixed stars as observed from Earth. And these 2 years have a difference of 20.4085 minutes. And in about 25,771 years, the difference amount to 1 tropical year, which is the actual year used in the world right now, because for farming and for climate purposes, seasons are maintained throughout the year. We also know from observation Earth's actual precession, that is the shift in the orientation of Earth's observed axis of rotation relative to the fixed stars in its orbit relative to the Sun, is called the precession of the equinoxes as well, because the equinoxes move westward relative to the fixed stars along the observed ecliptic, opposite to the yearly motion of the Sun along the observed ecliptic. while the Earth is rotating around its North Pole, geographic North Pole axis, its axial precession moves in the westward direction, opposite to the direction of the Sun with respect to the Earth. So from this observation, I reason that the circular orbit of the Sun, which is tilted with respect to Earth's orbital plane, is actually revolving in a counterclockwise direction around the z-axis, leading to this westward or clockwise revolution with respect to the North Pole of the Earth. And while the Sun is moving this way, its whole revolution plane is revolving around Earth's normal to its revolution plane. I have also depicted it here in this picture. So this is the Sun's revolution plane. The Sun is moving this way. And this is the precession of the equinoxes or actual precession, completing a cycle in 25,771 years in a clockwise reaction as observed from the northern hemisphere of Earth. That's what I propose. Another factor that comes as part of observation is that the Earth currently reaches perihelion, the point in its orbit closest to the Sun, in early January, only about 2 weeks after the December solstice. So winter begins in the northern hemisphere at about the time that the Earth is nearest to the Sun. It turns out that the proximity of the 2 days is a coincidence of the particular century we live in. The date of perihelion does not remain fixed, but over very long periods of time, it also slowly moves later within the year. And there is evidence that this long-term change in the date of perihelion influences the Earth's climate. This is because the orbital ellipse of the Earth in its motion relative to the Sun itself precesses in space, and this is called apsidal precession. The line joining the Earth and the Sun at perihelion moves eastward relative to the fixed stars in somewhat an irregular way. And it completes a cycle in various times jointly with axial precession, a time period from 20,000 years something to 29,000 years. And this is because there are various components affecting the perihelion of the relative Sun-Earth ellipse. And I am able to explain this with my circular orbit model. So the joint apsidal precession and axial precession period amounts to a little more, some thousand years more than 20,000 years, actually. How it is the Sun is moving eastward as observed from Earth. Axial precession is moving westward as observed from Earth. And the perihelion or the aphelion of the relative Sun-Earth ellipse based on the distance vector between the two is revolving also eastward as observed from Earth. Now, according to my circular orbit model, this is based on the L vector, the distance vector between the centers of revolution of the circular orbits of the Sun and Earth. here. It has three components, the LX, LY, and LZ components. And as part of my research, I have also calculated these LX, LY, and LZ components. This is the LX, LY, and LZ. These graphs are based on calculated data sets based on my mathematical formulas and analytical method that I have formulated, and Landsat data for the real sun-Earth distance observed for the particular time variant. So if we look at the LX, LY, LZ graphs, we see that for the current time, LX and LZ are correlated. And LY is almost constant with just some variation. And L is actually repetitive 4 times a year. And every quarter of a year, the LX and LZ components have 3 cycles, roughly, with some little peak components that impacts all these 3 components. So what I have this is the whole L, by the way, as a superposition of LX, LY, and LZ components. So here you can find the minimum and maximum values and dates of L for your information that I have calculated previously. So to be able to analyze and explain the apsidal precession, like the change of eccentricity and the shift in the aphelion perihelion axis of the relative ellipse for the Sun and Earth, I have defined 3 major components for the L vector between the centers of the Earth and the Sun's circular individual orbits. So one is the LXC line. It is not a line, but it's approximately a direction. The LX and the LZ component define this. The LY line, which is almost constant for now, for the century we are in right now. And also I define a third component, L3C, whose impact I cannot clearly explain right now, but it can be seen in all 3 components of L in these graphs. So according to observations in sediments around the world, the insolation variance components centered near the eccentricity-driven period of 100,000 years dominate most upper Pleistocene climatic records, and the unimodal 405,000-year orbital eccentricity cycle reliably paces back Earth's climate to at least 215 million years ago. There are also strong periods around 95,000 years and 123,000 years related to eccentricity, in addition to 11,000-year and 5,500-year periods related to actual precession. Computer simulations also show that Earth-Sun distance dramatically alters seasons in the eastern equatorial Pacific region in around 22,000-year cycles. And in addition to actual tilt, it is one of the drivers of annual weather cycles due to El Nino patterns. Looking at our climate change observations, the last glacial maximum, also referred to as the last glacial coldest period, is the most recent time during the last glacial period where ice sheets were at their greatest extent, between around 26,000 years ago to 20,000 years ago in Northern Hemisphere, and sometime between 26,500 years ago to 20,000 years ago in the Southern Hemisphere. And this is observed via radiocarbon dating. Deglaciation has caused an abrupt rise in sea level about 14,500 years ago. So coming to the subject of magnetic pole reversal, every several 100,000 years, the north and south magnetic dipoles of Earth swap locations, which is called pole reversal. Pole reversals are common in Earth's geological history, and paleomagnetic records tell us that Earth's magnetic poles have reversed 183 times in the last 83 million years. The periodicity in the polarity of the sediments is not observable in a very homogeneous sense, but on average about every 300,000 years, a polarity change seems to be observed in the paleomagnetic sediment records of Earth. With the current data, it is said that the last magnetic pole reversal occurred 780,000 years ago, though, but this might be due to lack of sufficient data or misinterpretation of existing data in sediments. There have also been temporary periods in which Earth's magnetic field has reversed globally for several hundred years, such as the Lachamp excursion about 42,200 to 41,500 years ago, during the end of the last glacial period, and the magnetic field weakened significantly. Earth's magnetic poles reversed, only to flip back again in about 500 years. These are called as geomagnetic excursions rather than full geomagnetic reversals, which are shorter lived, but there are significant changes that occur in the magnetic field's intensity. So looking at these dominant periods observed, I have sought the best joint model for the periods of the LXZ line, the LY line, and the L3C component, as well as for actual precession. And here's what I came up with. We already expect the precession of the equinoxes, the LXZ line and the LY line joint period to peak at 405,000 years. And we know that the precession of the equinoxes period is 25,771 years. That's the tropical year, completing one revolution in westward direction around the Earth. Looking for the joint period of precession of the equinoxes revolving westward and the LXZ line revolving eastward, because they are in opposite directions. The perihelion is moving eastward and the LXZ line is bound to impact that. Before each completes its period, they jointly cross at some point, and they have a joint period over 20,000 plus some thousand years. Making a calculation to have a near peak around every 100,000 years with a real joint peak at 405,000 years. We have found the joint period for the precession of the equinoxes and the LXZ line as 21,315.79 years. We now have the period for the precession of the equinoxes, which is 25,771.06 years. And we have their joint crossing period for TPXC. We can find the period for the LXZ line then, which turns out to be 123,298.93 years. This is actually very, very much aligned with the 123,000 year component for the eccentricity. So it's convincing that we're on the right track. The LY line is a secondary contribution to eccentricity and upside of precession. We expect it to be revolving opposite to that of the LXC line, because the calculations show us that in order for these components to meet at 405,000 years to form a peak effect, LY line has to be moving in the opposite direction to LXC line. And again, doing our calculations, we find that the period of the LY line is 566,195.94 years, which gives us the one peak component per 600,000 years, also aligned with observation. So looking at the joint crossing period of the LXC line and the LY line components, we very, very much to our surprise find the 101,250 years joint period, which is very near 100,000 years. It is no wonder around every 100,000 years there is a peak climate change or polarity-based effect around Earth's environment. Why it doesn't happen every 100,000 years is because the precession of the equinoxes does not always cross exactly on the same vicinity, but within 5,000 years, like a quadrant of the precession of the equinoxes and XZ line crossing. Moving on, we find the crossing period for the precession of the equinoxes and the LY line, which is 27,000 years. Now, the third component, whose effect we are not very much sure about, but obviously has some effect on upside of precession and eccentricity because it affects the perihelion and its motion as well, but in a minor sense. So we already have the period of the XZ line as 123,298.93 years. If we had a component that revolves in the same direction, that is eastward, as the LXC line as observed from Earth, and takes over and crosses it while moving in the same direction with a joint period of 405,000 years, we would obtain the period for this component to be 94,522.37 years, which is very interestingly so close to the observed 95,000 or 94,000 years component. So it seems we're on the right track for the third component as well. Its joint period with the LXC line is 405,000 years. They move in the same direction. And the precession of the equinoxes and the third component have a joint period of 20,250 years, whereas the third component and the LY line cross each other every 81,000 years. And this crossing period is the same as 3 times the crossing period for the precession of the equinoxes and the LY line, and 4 times the crossing period for precession of the equinoxes and the third component. And we also have that the crossing period for the LXC line and LY line happens at the same time when the precession of the equinoxes meets the third component 5th time after an initial lineup every 405,000 years. So we have a very perfect wrap-up of periods for these components. in the new model that I suggest for climate change and magnetic polarity change prediction. So let us have a look at our most significant results here based on the periods and the topology configuration we have found. When the LXC line and the LY line, together with actual precession, align again in 5,000 years after their initial triple alignment, and the L3rd component meets them at the same time, by the way, they are not positioned against the same fixed stars of the previous alignment as seen from Earth. In fact, the next time that they position against the same fixed stars of the previous alignment is crossed again by all four of them around after 7 alignments of 405,000 years. That is about every 2.8 million years, when all these four components come back to the same fixed start location as observed from Earth. This is worth noting, something to know. Now, we have found that the crossing period for the precession of the equinoxes and the LXC line is around 21,300 years, while they're revolving around the Earth's axis in different directions. Looking at the quarter cycles of this period, we can see that the LXC line and the actual precession line are in phase and out of phase every half cycle, that is around every 10,600 years or so. Now, the actual precession line is the June 21, December 21 line, meaning the solstice line at the points of maximum tilt. The reason that the alignment of the LXC line with the solstice line affects climate on Earth in a major sense is because the LXC line is the most important factor causing the aphelion of the relative Sun-Earth ellipse. So if the LXC line is in phase with the actual precession line, the June 21 date is when the Earth and the Sun are farthest from each other. But if the LXC line is out of phase with actual precession, the December 21 date is around the time when the Earth is farthest from the Sun. And this impacts climate. So when the precession of the equinoxes line and the LXC line are in phase, the maximum Sun-Earth distance occurs around June 21 as is now. So even though Earth is farther away from the Sun during the Northern Hemisphere summer, the Northern Hemisphere has hot weather due to Earth being tilted maximally towards the Sun. But the Earth's Southern Hemisphere is tilted maximally away from the Sun around this time, which is Southern Hemisphere's winter, and so Southern Hemisphere is expected to experience more extreme cold weather during this time. However, water mass is significantly much more than land mass in Earth's Southern Hemisphere, and as water heats and cools slower than land, Earth's Southern Hemisphere summer and winter weather does not swing between extremes and is milder than would be expected for Northern Hemisphere under a similar Sun-Earth configuration. And when the actual precession or the solstice line is out of phase with the LXC line, the configuration is just the opposite, and the maximum Sun-Earth distance occurs around the beginning of January, and the minimum Sun-Earth distance occurs around the beginning of July. Earth would be closer to the Sun as well as being tilted maximally towards the Sun during the Northern Hemisphere summer, and the Earth would be farther away from the Sun, as well as being tilted maximally away from the Sun during the Northern Hemisphere's winter. So, Earth's Northern Hemisphere summer and winter weather is expected to swing between more extreme conditions than compared to today. The precession of the equinoxes and the axial line being in phase and out of phase around every 10,600 years or so is aligned with the observation and computer simulations which show that Earth-Sun distance, in addition to actual tilt, dramatically alters seasons in the eastern equatorial Pacific region in around 22,000 year cycles of El Niño weather patterns. Another important configuration to consider is the alignment of LY line and the LXC line in phase or out of phase. The LXC line and LY line are in phase, that is superimposed, every 101,250 years, and the aphelion, thus eccentricity of the relative Sun-Earth ellipse, increases towards the maximum. And when they are out of phase, like some 50,000 years later or in between, their effects minimize each other, and the Earth's eccentricity is minimal. Some 1,000 years around those times when the LXC line and LY line are in phase, that is superimposed, every 100,000 years, when actual precession is also close to alignment with especially the LXC line, the climate of Earth would be expected to swing between more extreme weather between winter and summer, with glaciers melting, this extremity reaching a peak with total alignment of factors every 405,000 years. So with some logical calculation that I explain here, we have found that the current Sun-Earth configuration must be about 277,105.26 years or so after the last joint alignment of all components in this 405,000 year cycle. So it's about 13 cycles of the crossing period for the actual precession and the XZ line. Now, looking at our results regarding climate change, as we have found out that we are 277,105 years into the new 405,000 cycle period after the last initial lineup of the four components, about 23,980 years ago, the LXC line and the LY line were out of phase, completely aligning in the reverse direction and reducing each other's effect on shifting away the centers of individual circular orbits of revolution of Earth and Sun. So the eccentricity of the relative Sun-Earth orbit must have been a local minimum, meaning that Earth did not come close enough to the Sun any time through the year on average for insolation to be sufficient to melt ice sheets or glaciers, and a glacial maximum occurred. And therefore, this shows that our model predictions are consistent with observations on the last glacial maximum. Another supporting indication of the correctness and reliability of our model and analysis so far. There are four such times every 405,000 year cycle when the LXC line and the LY line are out of phase, completely aligning in the reverse direction and reducing each other effects so that there is minimal eccentricity of the relative Sun-Earth ellipse. And this is around 50,000 years, 150,000 years, 250,000 years, and 350,000 years after an initial lineup of four components every 405,000 years. And these are times when glacial maximums are expected to occur. And the next one would thus be in the 354,375 year timestamp after the last lineup, which is in 77,260 years or so from now. So there's quite a long time for that. But what is important here is that the period between these four occurrences is consistent with the 100,000-year pattern of observed glacial events. Thus, our model can predict the major glacial maximums. Also, looking at the future, if we wish to predict how climate will be changing in the next thousands of years, at about 5,000 to 5,500 years from now, we expect the Sun-Earth configuration to shift to a position where axial precession line opposes the LY line maximally, so that the Earth's northern hemisphere will be closer to the Sun around June, July, leading to higher insolation or hotter summer in the northern hemisphere, while it may lead to warmer winters in Earth's southern hemisphere, and the Earth's northern hemisphere is farther away from the Sun in December, January, leading to lower insolation and colder winter in the northern hemisphere, while it may lead to cooler summers in the Earth's southern hemisphere. In the meantime, the LXC line would be about 1/3 of a full cycle eastward relative to the last initial lineup position with respect to fixed stars, leading to Earth being much closer to the Sun between April-May and much farther away from the Sun around October-November. As a result, in the next 5,000 years, we expect gradually to have seasons swinging between more extreme weather in the northern hemisphere, from extended and colder winters to extended and hotter summers, with strong gusts of windstorms during seasonal change in spring and autumn, while the southern hemisphere is expected to have gradually more homogeneous and mild temperature throughout the year. So it might be a better idea moving to the southern hemisphere in the next few thousand years. So here we see the Sun-Earth system, magnetic field lines, and superposition, but not the scale, of course. Now, Earth's geographic North Pole is looking downwards, as in the calculation results of my circular model. The magnetic field lines leave the Earth around the geographic South Pole and enter the Earth around the geographic North Pole, but not exactly at the geographic north. So this is the geomagnetic dipole line, approximately. If we visualize the Earth and the Sun as rotating bodies of electric current based on their self-rotations around their own axis, we can infer the direction of their resultant currents due to their self-rotation motions, based on the resultant magnetic field lines of the Earth and the Sun and Biot-Savart law. As Earth's magnetic field lines enter Earth around its geomagnetic South Pole, near geographic North Pole, and leave the Earth around the geomagnetic North Pole, near geographic South Pole, it is as if there is a virtual magnetic dipole inside Earth with its south pole directed towards Earth's north magnetic dipole. See? According to Biot-Savart law and the right-hand rule, the resultant current of Earth due to its self-rotation must therefore be in a clockwise direction as seen from a vantage point above geographic North Pole of Earth. So it's east to west. East to west. While the Earth is moving in a counterclockwise direction, meaning west to east, this way. Similarly for the Sun, the resultant net current of the Sun due to its self-rotation must therefore be in a clockwise direction as seen from a vantage point above the geographic North Pole of Sun. So its magnetic field lines are like this. As a result, this is the Earth, actually. It's North Pole, the geographic North Pole looking down, and magnetic field lines moving like this. And at the same time, the sun's magnetic field lines come in a tilted manner and shift the magnetic field lines of the Earth with a tilt. We explain based on our circular orbit model. That must be why the magnetic dipole of Earth is shifted, because of the sun's magnetic field lines being stronger and pulling the Earth's magnetic field lines with a tilt based on their equatorial plane's tilt. Based on this model, we can further reason that the daily variation in which the Earth's north magnetic dipole describes a rough ellipse with a maximum deviation of 80 kilometers from its mean position should be because the landing point of the sun's tilted magnetic field lines upon Earth drifts over a day in this pattern as the Earth rotates about its own axis. So it's more understandable when we think of the Earth and the Sun revolving on individual circular orbits. Based on our circular orbit model and our analysis so far, we are also able to assert that the reason for the Earth's magnetic pole shifts and reversals over tens and hundreds of thousand years must be due to the changing topology of the Sun's individual circular revolution orbit relative to the Earth's individual circular orbit. Based on the cycles of axial precession, the LXC line, the LY line, and the L third component, whose periods we have already found based on my model. During a magnetic pole reversal work, there must be some sufficient external magnetic field effect to flip the resultant magnetic field of Earth and change the direction of Earth's resultant electric current regardless of its self-rotation direction. So the sun's tilt and distance relative to the Earth must be such that these magnetic field lines have to be separated from their normal position maximally, causing a flip at some point. For instance, whenever the LXC line and the LY line are close to being out of phase, that is when they are topologically in reverse direction with respect to fixed stars, the distance between centers of individual circular orbits of the Earth and the Sun are minimal, so the eccentricity of the relative Sun-Earth motion ellipse is minimal. And this leads to average Sun-Earth distance over a year to be less compared to other times, such that the magnetic field lines of the Sun landing on Earth must have a stronger effect. And if at the same time axial precession is aligned with the out of phase LXC line, LY line, the Earth is maximally tilted towards or away from the Sun, so that the Sun's magnetic field lines landing on Earth have the largest angle separation away from the Earth's geographic poles, pulling and tearing away Earth's magnetic dipoles strongly from their locations around geographic poles, which we suspect may coincide with the times when magnetic pole reversal occurs. As we have found that we are around the 277,000th time step in the current 405,000 cycle, the occurrence of the Lachant excursion around 42,200 years ago would be about the 234,905 time step after the last lineup, which is a little after when axial precession aligns with the LXC line 2 cycles ago or their crossing period, also coinciding with a time when angular separation of LXC line and LY line with respect to fixed stars is about 0.64 pi. And that corresponds to one of those times of minimal distance between centers of individual circular revolutions of the Earth and the Sun, which can roughly be estimated in XY direction, as we have the minimum and maximum values of LXC LXZ and LY. As a result, this magnetic pole reversal time is in agreement with our analysis, and thus our circular orbit model and also our LXZ line, LY line, axial precession line model is able to explain the possible cause of Earth's magnetic pole reversal phenomenon topologically. So what is left to explain here is the precession of the ecliptic, and it is actually totally explained by our circular orbit model, because what determines the observed ecliptic, which is a virtual plane formed by the relative Sun-Earth motion, is the distance vector from the Earth to the Sun that moves through space throughout the year, according to our circular orbit model. And the observed ecliptic is not a two-dimensional plane, but it sweeps through a three-dimensional plane as the centers of individual circular orbits of the Earth and the Sun shift periodically based on the change of L vector, while the Earth and the Sun are moving along their individual circular orbits throughout the year, as well as through tens and hundreds of thousand-year cycles. The periodic up and down drifting, which has recently been observed and called as the precession of the ecliptic or planetary precession, is therefore consistent with our circular orbit model, and it was measured to have a period of around 100,000 years also, relative to the invariable plane, the plane that represents the angular momentum of the solar system. And this is similar to the 100,000-year eccentricity period. And this is aligned with our crossing period of the LXZ line and LY line, over which the relative Sun-Earth eccentricity goes through a cycle between a maximum and a minimum, when these two lines are in phase and out of phase, thus causing the angle of distance vector with respect to Earth's equator precess between a maximum and a minimum, leading to the precession of the ecliptic observation. Here we have tried to picture this. So this is the Sun's orbit centered with the Earth's orbit, but it's not like that in reality. When this orbit is shifted this way, this is the June 21 point and December 21 point. When it's shifted this way, normally when the Earth to Sun distance vector is like this, it extends here, thus the angle between the equatorial plane of the Earth and the distance vector is less. So when the Sun-Earth ellipse is more eccentric, we expect less tilt, and we expect Earth to be less tilted towards or away from the Sun. And when the solstice line or axial precession line is revolved one half cycle, so that December 21 is here and June 21 is here, this time we have the Earth to Sun distance vector like this, and the angle between the Earth's equatorial plane and the Sun's tilted orbit is much more, and this is how the Earth's tilt angle precesses between a minimum and a maximum as the axial precession axis revolves and the LXZ line between the centers of the Sun and the Earth revolve. So overall, we can conclude that our new circular orbit model and our analysis so far on how axial precession, the LXZ line, the LY line, and the third component vary in every 405,000 years cycle all provide a logical explanation on how the resultant Sun-Earth topology potentially impacts Earth's major climate change and magnetic field shifts and reversals over tens and hundreds of thousand years, equipping us with more insight into actual mechanisms by which these heavenly bodies abide, and with a tool to predict in which direction Earth's climate and magnetosphere is traveling. to be more prepared for humanity's future environmental living conditions and even existence in the future. The analysis in my paper and this presentation also reinforces our previous assertion that the Sun, the Earth, and the Moon, as well as all heavenly bodies moving in space, must each be revolving in their individual circular orbits, but seeing their relative orbits elliptic, hyperbolic, or parabolic. Thank you for listening.